This tutorial explores the topic of lithium-ion batteries, on-site measurements, within the framework of the European project titled Personalized Education in Measurement Science and Technology, Empowered by Machine Learning. In real applications, cells are often stacked in series to make a battery pack with a suitable voltage and energy. As an example, battery electric vehicles might have 96 cells in series for a total voltage of approximately 350 volts and an energy range between 50 and 100 kilowatt-hours. Inside a battery pack, cells are first organized in modules and then stacked up. The battery pack is connected to other loads, such as the traction inverter or the onboard charger, by means of contactors. The contactors serve to disconnect the battery while the vehicle is not operated for safety reasons. There are two main contactors, one on the positive and one on the negative pole of the battery. Additionally, there is a pre-charge contactor with a series resistor to limit the in-rush current when the battery pack is connected to the loads. The battery management system is the electronic control board with the responsibility of monitoring the status of all the cells inside a battery pack. The PCBA is divided into two parts, the logical part on the right, which operates at an extra low voltage of 12 volts, and the sensing part on the left, which measures the voltage of the cells. The two parts are galvanically isolated and communicate by means of isolation transformers. The BMS implements multiple functions. The main function is to monitor the current, voltage, and temperature of the cells. Such information is necessary to estimate the state of charge, health, and power. Other functions include the measurement of the isolation resistance and the detection of loss of isolation, the management of relays, cell balancing, and thermal management. In addition to the centralized BMS architecture presented in the previous slides, for larger battery packs, the distributed architectures are often adopted. In such a solution, the sensing boards are separated from the main logic board. The communication can be either wired or wireless. Cell measurements are performed by means of specific ASICs, application-specific integrated circuits. These circuits implement the necessary redundancies on the measurements of voltages and temperatures and diagnosis in order to satisfy the functional safety requirements. The communication between ICs is galvanically isolated by means of isolation transformers. Cells in series are crossed by the same current. Due to the different capacities of the cells caused by part-to-part variations, the state of charge of the cells is not exactly identical. To avoid the weakest cell being the bottleneck while charging, a function called cell balancing is discharging on purpose the cells that have the highest state of charge in order to maintain the state of charge uniform across all cells in the battery pack. Active balancing recirculates the energy from one cell to another, but it is also costly and bulky due to the electronic components involved, specifically inductors. Consequently, passive balancing is the most adopted solution, especially in automotive applications that require low cost and low weight. Implementing electrochemical impedance spectroscopy in the field is one of the latest industry trends. In fact, EIS allows for gathering deep information on the state of charge, temperature, and aging of the cells. This function is employed by stimulating the cells with an alternating current stimulus, created from loads such as the inverter, onboard charger, or DC-DC converter, and analyzing the voltage response of the cells in the battery pack by means of fast Fourier transform or similar methods. The current and voltage waveforms are analyzed in the frequency domain, and the impedance can be estimated at multiple frequencies. The internal state of charge, society, of a cell cannot be directly measured. It must be estimated by means of a state observer, based on externally measurable signals, such as voltage and current. One common method is the Coulomb counting, which integrates the current in time. However, this method is negatively affected by any offset in the current sensor and requires knowing the initial state of charge. To estimate the internal condition of the cells, state observers, such as the Kalman filter, are mostly adopted. In addition to that, recently, artificial neural networks have also become popular as they can potentially achieve better accuracy for the estimates. The Kalman filter method compares the measured voltage to the voltage predicted according to the mathematical model of the cell. The variation between measurement and model prediction, called the innovation, to correct the estimated value, for instance, the state of charge. Neural network methods estimate the internal state starting from external measurements. In order to be effective, they require training with a massive amount of data. On the other hand, it is believed that neural network can detect dynamics that are not modeled by the standard cells, models, therefore they can potentially achieve higher accuracies. Here you can see a list of references that can be used in order to further explore this topic. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Nice and Politecnico di Milano, within the framework of the European project, Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.